I have so this is where our this is a Jupyter notebook, by the way. So my Jupyter notebook is in this directory, and I also have a a directory called data in it. So that is where I've kept this file called this ugly name, whatever. But this is where the file is. So this when you use Jupyter notebooks, it assumes that whatever directory the notebook lies in, that is your base directory, you could say. So you just need to add whatever is ahead of this directory. You just need to add the name. So data slash the file name. So that's how you do it. In case it's in even more folders, like there's a folder and a folder and a folder. Just keep adding the names. And in case you want to go backwards, I think before this you can add like 2 dots or 1 dot or whatever, something like that. But it's not a big deal. So this is how you open the fits file, and then essentially you're storing it as an object. And this object, let's call it HDU list. So header data unit list, I guess that would be the full name of it. But yeah, I'll call it HDU list. You can call it whatever you want. No restrictions there. So what is HDU list? Let's see. They've given a spoiler below, but let's see what it is. So it seems like some kind of list-like object. So it's not a list, but something different. It's some AstroPy object. But let's see what more we can extract from it. So since it's like a Python list, let's look at how many elements it has or whatnot. So if we do hdulist.info, that gives us the information on the layers to the Switch file. So if we do that, I don't think there's any change here. I've already printed it out. But so we have the primary header, as you can see here. It's always arranged, it's like hierarchical, you could say. So the primary header always comes first, usually, I think. So this is the primary header. Well, the name is primary, so let's take the word for it. Just keep a note of the dimensions here. So this primary header has data under it that has this dimension. So keep this in mind. And then we have another thing called energies, which is we don't know what exactly it is, but it looks like it has 30 rows and 1 column. So let's see. Let's investigate a bit more. Looks like our image data is stored in the primary header. Well, yes. How else do you think an image will be? Will it be 30 rows and 1 column? This seems very, it seems like a table rather than an image. And here, well, here it's kind of it's a mixed bag, because usually you think of images as a 2D object, right? 2 dimensions, but here there are 3. But let's see. This is most likely the image. So let's investigate this further. Uh, Here we use HDU list of 0 for, and this is how we extract the primary header. So this number, just use that. So HDU list of 0, similar to how we, extract elements from a list. I hope you attended the Python session. I mean, the intro to Python session. So we extract the first element, you could say, and we store it as HDU. You can call it whatever you want. Let's see what this looks like. So okay, again, it is an AstroPy object. So if it wasn't evident why this thing why this thing looks like a list, here's an object, comma, another object. And as we can see, there are 2 things here. There are 2 layers here. So that's why I said it's like a list. Okay, if you have another fits file with multiple headers, let's say 3 headers, then you could say that this will have like 3 objects in the list. So we've taken the first object, the primary header, and again, obviously, it gives us this object. Now let's further investigate this object. So this object will also have some methods associated with it. Let's take a look. So this mysterious object that we've named HDU has 2 attributes that are of importance to us: data and header. So let's take a look. Let me extract the data by using HDU.data. So let's store it in under image data, foreshadowing by the way. Then we will print the shape of this. Okay. If you're wondering how did I know this is something which has shape or whatever, uh, don't worry about that. Image underscore data is for showing it. This is a Jupyter notebook, so uh, the the last line is usually printed unless you put a semicolon at the end. In that case, it doesn't. It only printed the shape of this the HDO data. In case you want to show this image data, just remove the semicolon. This is a cool trick for Jupyter notebooks. Yeah, here it is, and this is what it looks like. So here we see something like a two-dimensional array arranged, and then after that we have another two-dimensional array, and then after that we have another two-dimensional array, and it seems like this dimension that you see here, 30. It seems like there are 30 two-dimensional arrays arranged like this. So this seems like an image. This seems like there are 30 images arranged, arranged in this order. You could say side by side, not side by side, but on top of each other, right? If you can visualize how this data structure will look like. So this is where our image lies, and these 30 things. So you can probably guess like why we have 30 here. As I said, if you observe things in multiple wavelengths, and you want to like access the intensities that you observed at this particular wavelength, you need to choose one of these images, one of these out of these 30 images that you have. So let's further investigate. you know HDU. So this is the HDU.data. This is the attribute HDU.data. I mean, this is the data attribute, sorry. So what about the header attribute? Let's see. HDU.header. We get a bunch of this. Uh, it might look overwhelming at first, but you just need to, look for things that you look for familiar words. So the first thing that we see simple. Let's not worry about that. Even I have no clue what that is. But number of axes. This seems like we've seen this here, right? There are 3 axes here. So it looks like this header file is giving us information about the data that's present. So if we go back to this structure here, sorry for the back and forth, but it seems like each of these objects in the fifth file, it's grouped it's taken in pairs. So the primary header along with the data is the first object, and then any objects after that will be the extension header along with the data associated to the extension header. So this is a cool system, right? You have data, but this data also requires metadata in order for useful use. I mean, useful use. Oh, okay. In order to be productive, because you don't know if you just have a bunch of arrays, of some, 3, 4 dimensions, and you have no clue what these dimensions represent. You'll be, it's kind of troubling. There's no point of using such a complicated file format. So that is the reason why we have header files. They give us information about the data that we have, and we can arrange uh, multiple layers, and we can store a bunch of data. So let's say this is the data for one particular part of the telescope. Let's say the telescope is very nuanced, has like 3 different portions corresponding to some different mechanisms or whatever. So let's say this is one of them. Can you give me a second? I'm really sorry, someone's at the door. Okay, I'm back. Sorry about that. I'll continue. So yeah, so as we said, as we saw, the data and the header come together as a pair and are stored as a pair in an object in this HDO list. This list basically. So as we go on, we saw the header file and we noticed that it has 3 axes. So it's just talking about the data that we've extracted here. So let's see if it gives us any more information about what this uh, data actually is. So here we see that the axes, they're all right. Everything's matching. So let's go on. So we see this CR value, value of longitude in the pixel. Okay. Let's keep going further, and then see type or whatever. So let's this might be the value for the pixels or one of the axes. Let's see. We don't know for sure. We see that it has a unit of degree. Okay. And next we see that this has this CR val 2 is like a latitude. Okay, latitude and longitude. Mhm. Might lead to something. And we see that the third unit, you could say the third unit has a value of energy. Okay, so we kind of get a picture here, right? We have the latitude and longitude, the latitude and longitude values basically giving us information of the position, right? And then we have the energy of the pixel. So, and the third, it has a unit of, the mega electron volts or whatever. So we kind of get a picture here, right? What these, these dimensions actually mean. So let's get a clearer, let's actually plot the picture in order to, confirm our suspicions. So let's now plotting the image of the FITS file. This is the fun part. To plot the image data array, we can use matplotlib, but which function is best for the job? So if you use scatter plot or something, I mean that itself is two-dimensional. An image is an image is essentially three-dimensional. You have the data about the coordinates of the pixels and then the each corresponding pixel value. So there's something called image show, a function in matplotlib.pyplot. So this is, made for generating images, for visualizing images. So let's just, throw in our image data into this image show function. Let's see what happens. So here I'll import numpy because we'll be dealing with arrays, so it's, useful to have. Let's do print of image data of 0 first. As you can see here, if you recall slicing arrays in Python. So here our first dimension has 30 elements in it. Okay, so this is most likely the image, and we have 30 images arranged. So let's just look at one of them, because if I put 30 of these, the image show function won't work. Okay, so we have 30 of these. Let's take the first one. By that, how do we do that? We use this. We access the first one with this index. The first one will start with the 0 index, and then after that we use a colon to represent the fact that we are calling every single entry in this dimension of the array, along this dimension of the array, as well as this direction, both the direction. So what it does is it looks at the first element along the first dimension, whatever you can call it, the first dimension, since it's arranged like this. uh, where did it go? 30, 360, 720. So the first dimension, we take the first element, and then the other two dimensions, we look at all the elements. So think about it as like 30 images. You're just pulling out the first image and looking at it. Okay. So next we define something. You can call it whatever you want. Let's put something more formal, very original, but okay. I call let's make a NumPy array. So we take image data, and zeros like what zeros like does is whatever structure that this image data of this zero blah blah blah. If you want, we can even we can do something like this for parity. So yeah, this is we'll call image zero the image data that we extracted from the bits file. Then we create a NumPy array which has the same structure as this image zero. I'll remove this, which has the same structure as this image zero, except all the entries in this array are zero. That's why it's called zeros like. Next, what we do is, since we saw that image data, its first dimension has 30 entries in it, right? Let's iterate through those entries. So for I in range 30, Python Python is very easy because a lot of the syntax, it's almost like readable in regular language. Like it's kind of how English works. So for I in range of 30, so I will basically take values in the range from 0 to 30. Not actually 30, it's 29 because it goes from 0 to n minus 1. Okay. So for I in range 0 to 29, okay, we'll go through each one. We'll iterate through each one. So I've removed bra. I've called it image now. So let me just, write image. Plus equals to it's used in other languages as well, but basically it's the same as writing image is equal to image plus image data of this. So whatever you write on the right hand side here, it's added to the original thing, and that transform the original thing. So for a more demonstrative way of writing, it's essentially the same as this. Okay. So for the first iteration, we see that this will be an array with zeros, and then to the array with zeros, we add image data of I. So we add the first picture, we add that to the array of zeros, and then we keep that as it is. We store that as image again, and then every iteration, it keeps happening. We are basically adding the pixel values from each slice, from each of those 30 slices. Okay, why are we doing this? It's just for demonstrative purposes, but let's plot one of them as well. So here I've essentially the word here I should use is stacked. I've stacked all the images together, and I've plotted it here. So I'll write image. Image is the thing that I want to plot here. So if I plot that, this is what I get. Okay. Looks kind of cool, and you can, since this is a figure object from matplotlib. So sorry, it's an image object. You can use stuff like you can increase the size and stuff like that. I won't do that here, lack of time. But I hope you can see the image here. It doesn't look too fancy, but this is what I got after stacking all those 30 uh, those 30 images that were available in our data here. So we can add one more thing called color bar. Color bar, what do these colors represent? Why is there just random color? If to in order to know the pixel value for these colors, we have this color bar here. So you can tell that the more blue it is, the lower pixel value, and this is the roughly the range. So this is the pixel value range. And yeah, this is the way we plotted, we stacked all the images together and plotted this. Stacking is a useful tool while, doing astrophotography and astronomy in general, which is why I've used this for demonstration purposes. But instead of this, let's do something of, let's just take a look at the first slide, right? So if I do that, you can see a slight difference, if we, want to look at some other slides, let's say, oh, sorry. Say, you guys can choose, but whatever 6, let's say. Let's look at 6. This doesn't change because we are just adding, everything together. This will change. Let's see if there's any noticeable difference. Okay, slightly. I can see more towards the right, more towards the left. So essentially, I've composed all the images together, all the 30 images to get this, but you can extract each of the individual images as well. So yeah, this is how you use open FITS files. This is how you plot the images from the FITS files. So the essential work, the procedure that you should follow is you should, get the HDU list. From HDU list, you can use info to get each of these header data pairs. Okay. To get info on these header data pairs, you use dot info. After that, you choose your the header data unit. Okay. We chose the first one. After that, the two attributes that we deal with here are data and header. For getting the data, you just do dot data. For getting the header, you just do dot header. Now the procedure is you look at the header data, understand what's happening, and then try to assign meaning to the image data that you have here. So after that, you can go ahead with plotting because you have a clear picture of what you're plotting, rather than just going in blindly and getting errors based on dimension here. So that's how you plot the FITS files. And now we'll move on to coordinate systems. Let me just check the time real quick. Okay, we have a bunch of time. So celestial coordinate systems, if one were to begin the pursuit of studying the heavens from scratch, they would promptly realize the need for an elaborate reference system to record the positions of celestial bodies for one's own bookkeeping, but also for sharing their findings with others, as I said initially, right? Hence, it is important to understand the coordinate systems used to map the sky to do most of astronomy. So one of the, the first and foremost concept that you should know while dealing with celestial coordinate systems is the celestial sphere. First of all, the celestial coordinate systems, they're a little bit tougher to understand, from regular coordinate systems that we deal with, even, spherical, because essentially it's just a spherical polar coordinate system. But there's the issue of, what you consider as, the reference. What is phi is equal to 0? What is theta is equal to 0? Deciding what is phi is equal to 0, what is theta is equal to 0, that is where the nuance comes here in these celestial coordinate systems. Or else essentially they're just spherical coordinate systems. So with that, let's move on to the first concept, which is called the celestial sphere. Nothing too fancy, but essentially just imagine a shell around the Earth, or even you, for instance. Just imagine a shell around you. Okay, it encapsulates you completely. Now, just extend that shell outwards. Keep extending it. Keep increasing its radius, so it becomes like a massive shell. Or that shell could probably encompass our Milky Way galaxy as well. Doesn't matter, but basically make it a massive shell. All right. Now, you can, that shell, if the celestial bodies that this shell passes through, you can just, as soon as it passes through a star, you can say that star leaves a stain on the shell. If you get what I'm trying to say here, right? If you're pushing the shell outwards and the shell passes through a star, that star leaves an imprint on the shell. Okay, and no matter how large the shell gets, that imprint will remain. So that is essentially how the celestial sphere concept works. So another way of saying it would be the celestial bodies are projected onto the sphere. All right. So since the radius is of arbitrary, we only need two coordinates to specify the position of any body, right? Any body on the sphere, any body as in the imprint, as I said, of the star or whatever, any object. So we only need two coordinates. And since this is a sphere, the obvious thing would be, spherical coordinates, theta and phi, some two angles you need. So this is the basis for all the coordinate systems that we are going to discuss, with the only differences being the centers and references from which we measure the two coordinates. I hope it should be clear by now. So now the coordinate systems that we'll be looking at are the horizontal system, equatorial system, ecliptic system, and galactic. If you engaged in any amateur astronomy or whatever, you might have come across the horizontal system as well as the equatorial and maybe the ecliptic system as well. But the horizontal system is probably what you've heard of the most. So I'll move on to that now. This is also called the altitude azimuth system. So how this works is you're wherever you are on Earth, imagine a tangent plane that passes through it, okay? Or essentially the celestial sphere that you've created, you are at the center of the celestial sphere, all right? Now you are at the center of the celestial sphere, what will be the equator in some sense of the sphere, from your perspective? It'll just be a tangent plane. Basically, from what you see, it'll essentially be the floor, like the ground, right? Because we don't see far enough to observe the curvature of the earth, but you should think about it as a tangent plane. Wherever you're standing, the surface beneath you, that will essentially be your the equator for this celestial sphere. All right. So any anything that you measure, above this, like if you want to measure how high an object is when compared to this equator, you will use a coordinate called altitude. This essentially corresponds to, if you think about spherical coordinate system, it'll correspond to theta, except theta, it's defined usually from the z-axis, which will be, vertical. But think about it starting from the xy plane or whatever. If you're following what I'm saying, but doesn't matter. Essentially, how high the object is given by the coordinate called altitude, and where the object is with respect to north, south, east, west. You can wherever you're standing, you can find north, west, east, and south. You can find those directions right on Earth. So okay, we'll get to another thing, but you can usually find where is north, where is west, where is east, where is south. So with respect to them, where is the object? How east is an object, how west is an object. That is given by the azimuth. Okay. So the reference for the altitude is clear, right? If the object is located on the horizon, so let me ask this question. I hope in case people are following, what will be the altitude for an object which is on the horizon? I mean, if it's on the horizon, you probably can't see it, but still, if you know that the object is located there, if you know that a star is right on your horizon, what will be the altitude for that? You can answer in the chat box, or you can uh, turn on your mic and tell me the answer.
0, obviously.
Yeah, exactly, it'll be 0, right? But what about the azimuth? How do you choose for that, right? Can you does anyone have a suggestion, or is it very arbitrary?
Do we set a star as reference?
Okay, the setting star as reference is a good idea, but it happens in the later coordinate systems. Here we can use something much simpler, okay, which also has a drawback. I'll get to that, but you can choose essentially either the direction pointing north, right? As I said, think about this as you are the observer. You're on Earth, any point on Earth, and then you can find the north and south directions, right? So choose the north as the reference and measure angles starting from the north. And you can go anti-clockwise, clockwise, as you can see in this diagram. I hope you know, the clockwise, anti-clockwise thing is clear. So we start from north. So anything that will be directly in the north, right? Any object directly in the north, that'll have that'll have an azimuth of 0. Okay. As it goes south, it becomes 180, and then it's like a circle, so it can go above 180 as well. So I hope that's clear now. So essentially, we need two things. We need the altitude and the azimuth. The azimuth, gives you the leftness, rightness, so to say. If you look at it from, if you want to visualize this thing the best way, if the diagram isn't clear enough, think of yourself in an empty field, right? No trees, just grass beneath you and the sky above you. Okay. How to look around you 360 degrees, you obviously need to rotate yourself, but essentially where how much you need to rotate yourself, that is given by the azimuth, and how high you need to look, how high you need to tilt your head up, that is essentially the altitude. This is how this coordinate system works. And as you can probably tell already, right, the thing about this coordinate system is, if someone is located on another place, on Earth, let's say they're like, you're in Chennai, another guy is in Delhi or something. you'll realize that, your coordinate systems don't really match, right? How can they match? Because the tangent planes are different for both of you. The zenith will be, so I didn't mention what the zenith is, but essentially it's the highest thing in the sky. You can only look up, like, perpendicular to the ground, right? You can't, there's no meaning to higher than that. So the azimuth, as I mean, sorry, the altitude, as it, might be obvious now, it'll have a maximum value of 90 degrees, right? And also things below you will have negative altitude, so you can have minus 90 as well. The thing above you, okay, above in the sense, like, if you have to put your head up, right, that is called the zenith. And if you have to look, completely down, you have to look through the floor, essentially, okay. If you have to look through the floor vertically downwards, that is called the nadir. These are just terminology, not that important. But so we reach a question. So as I said, right before that, if you have a friend located in Chennai and you're in Delhi, your zeniths will be different, right? Even your north and your north, east, west, and stuff like that will also be different, because Chennai and Delhi, I think I can say for sure that they don't lie on the same longitude. So they won't have the same, they won't have the exact same north and south. I mean, not north and south, north, west, east, stuff like that. So that's why you will have a different altitude and a different azimuth based on the location you're in. So this is what makes this, like an iffy system. But if you're with your friends, if you're, we are all back in campus, we are having a horizon observation session. We're all, sitting on HSV terrace, and someone observes, like, some star, and he wants to tell us where it is. When someone is using a telescope or something, then that is the time when we can use this system. That is when it's the most useful. All right. Then he can say, this much altitude, this much azimuth, and you need to know where is north and south, but that is not a big deal. You can probably pull up your phone and find out. So yeah, this is the use case for this coordinate system. Are there any questions? I hope this is clear. So if this is clear, I have a question for you. What happens at the north and south pole? How would you use the system at the north and south pole? Can you use the system? This is the question.
Could you come again?
So the question here is, what happens? Can I use the system at the north and south pole? So imagine yourself like directly on the north pole. How will I use the system? Can I use it? Give it your best shot, like anything. If you think you can still use it, just say yes, no problem.
I mean, if you're at the North Pole, you won't be able to see the like stars or systems that are below a certain angle, right?
Okay, that's kind of like that's the thing everywhere, right? If something, from your perspective is below you, you can't really see it, but there's still merit in, identifying where it is, right? That is what we want here. Even if it's below your, field of view, like, it's below the ground, essentially,
Yeah.
you can still mention where it is. That is important. So that, some other person, okay, as I said, this is only used when you're in the same location, but still, yeah, that is not the
I think we
issue
can
here.
use it.
Can we tell that it's usable but like least effective at the poles?
Why would you say least effective?
Because like the we can't really define one set of angles. Here we are like having two sets of like 0 to 360 angles. When we go to the poles, one of it will be limited to 0.
Okay, I think you're going along the right direction. If someone else can word it a bit differently, I think you're on the right track, actually.
There won't be any northeast, southwest at
Exactly.
the.
Yes, exactly.
Yeah, so
If you're
that
at the
is
North
what I
Pole,
defined as the one set of 0 to 360.
oh, okay, yeah, that's why I kind of like, got it that you were in the right track. Anyway, like, good job. Essentially, if you're at the North Pole, everything's towards the south, right? And if you're at the South Pole, everything's towards the north. So how do you define the reference? So at the North Pole and the South Pole, this is like a test whether you've understood this coordinate system. Basically, the azimuth is undefined. You can still define the altitude, but only the azimuth is, undefined. That's it. So I hope that's clear by now. I didn't check the chat in case anyone did. Okay, Adit Mahajan, he got it right. Uma Shankar has a question. What is the use of zenith and nadir? That's just like, it's just terminology. Like the highest point and the lowest point. That's it. There's not much to it. Just take, fancy words. That's it. All right. Okay. Now let's move on to the equatorial system. So analogous to the latitude longitude system we use for Earth, the equator is taken as the reference plane. So again, celestial sphere, the equator is taken as the reference plane here. Rather than, if you're, let's say, in one of the northern hemisphere countries, rather than taking your tangent plane, the tangent plane to the Earth as the reference, we're taking the equator itself, the regular, the geography, the thing that we define in geography, that equator. We take that as the reference plane, essentially reference plane as in, this is where we'll measure the altitude from. I'm really sorry. Once again, I'll just be right back. Do ask any questions in the chat meanwhile. Yeah, sorry about that, but yeah. So equator is the reference system. Essentially, the thing that will correspond to altitude, as we'll see, that is measured from this reference that we have. Everything above that, you'll give it the positive value. Everything below that, negative, and it'll go from 0 to 90. That'll be the range. Okay, that is the reference plane. Now, so we define this as, what's written here? Thus defining the north and south celestial poles. Okay, so celestial poles are essentially, so they're analogous to the zenith and nadir that we have here, right? Celestial poles are, the north celestial pole is the thing that's vertically above you. Don't get confused by the use of north here and north here, right? Here it's like we've increased the scale, essentially, like increase the scale. That might be a confusing way to say it, but we're looking much more beyond now. It's not restricted to you. We are looking like, the earth is almost the center here. Not almost, it is the center here. So essentially, uh, the the equator, right? Yeah, the thing vertically above the equator, that will be the north celestial pole. Okay, the thing that is vertically below the equator, that will be the south celestial pole. Now, let's see. So since we've defined this north celestial pole and south celestial pole, we have, a sense of up and down. So we can define an angle there. That angle is called declination. So as you can see, this word here, parallels of declination, essentially like a latitude. It's like a latitude, except, bigger scale, okay, not galactic scale, that'll come later, whatever. But yeah, it's essentially like latitude. Okay, that's why we have these parallel lines, 0, 15, 30, it increases in steps of 15. So yeah, that is about declination. And now again, the same question arises. What is the reference for the, something analogous to azimuth, right? So for that, we'll call that right ascension firstly. Rather than using the term azimuth, we'll call it right ascension. The right ascension is measured from the sun at March equinox, the first point of Aries, which is the place on the celestial sphere where the sun crosses the celestial equator from north to south at March equinox. So this is a lot of fancy words, but what this says is, so you do know that the Earth is tilted, right? Because the Earth is tilted, it doesn't exactly lie in the plane. So the fancy thing about our solar system is all the planets roughly lie along the same plane, right? They're all in the same plane. Okay. The thing is, the Earth is slightly tilted. It's not, the equator is not exactly in this plane. So the Earth is slightly tilted. It has that, okay, I just forget the value, but it's like 24 something, right? The tilt. Uh, yeah, basically that tilt is there, right? Because of that, if we look from the Earth's perspective, the sun actually isn't, it slightly goes in an angled manner depending on the time of the year. Okay, the sun doesn't rise exactly to the same location every single day. That and that by that I mean you're in the same location the entire year. You know, if they light in the same plane, you would see the sun rise up to the same spot every year. Okay, but what happens is the sun slightly moves throughout the year, and what happens is if you look from the perspective of Earth, okay, you will see that the sun moves along this green line essentially. I hope you can see it. I hope the quality is good enough. But the sun moves along this green line, and the point where in March specifically, because it'll basically cross the equator. Our equator, like equator as a reference, the sun will cross the equator at 2 points in time. Okay, but we choose the one in March as the reference here. So basically, in March, when the sun finally crosses the equator, we call this the vernal equinox. Okay, and this vernal equinox, we've taken it as the reference for our right ascension, basically uh, uh, the analog to azimuth, as we've seen before. All right, I hope that's kind of clear now. And then about some conventions. So these coordinates can be used irrespective of location and time to a certain extent, I believe. Yeah, you can use it irrespective of time as well. This time thing is because like, okay, doesn't really matter, but the Earth also, our whole thing is moving. The solar system is moving, blah, 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 whatever. Don't worry about that. But it can be used irrespective of location, which is why this is one of the most used. So I don't know if anyone has done some, amateur astronomy stuff, but you'll see a lot of right ascension declination, a lot. Like, when you extract data or something, they'll probably have, the star position mentioned in terms of right ascension and declination. Okay, so here some terminology, I mean some conventions. The right ascension is represented in the unit of hours, not time. I mean it's not time per se. It doesn't really represent time, but essentially the convention arises because there are 24 hours in a day, right? So since the Earth rotates, right? Basically the Earth rotates, you can chop the entire 360 degrees, right? You can chop it up in terms of hours. That's how the convention arises. Whatever, but basically the 1 hour of right ascension is equal to 15 degrees of the celestial equator. Like just you know if you want to convert it into degrees, that's how it works. But usually the convention is the unit of hours. Okay, don't worry about it. It's not something very fancy. So I hope this is clear. Let me just check chat. In the North Pole, can we use a longitude as a reference for azimuth? So the way the system is defined, right? The way we define the system, we don't really use the word longitude, right? So we define the system, the way I defined it here. That is the entire definition. And then I've tried using it at different points on the Earth. The only place where it fails, where it's not defined is the North and South Pole. You can do something to remedy that. Somebody out there has definitely done something to remedy that. And maybe your suggestion about using longitude is right. But again, you define longitude with respect to, the longitude reference. How is it defined? Does anyone know? Go back to, your 9th standard geography, I think. 9th standard only, probably. Yeah. TBSC.
Red meridian.
Exactly. Yeah. That London thing, right? So that's where we get the Greenwich meridian, blah, blah, blah. That is how our longitudes are defined. So the question you can ask there is like, I mean, why even use this north-south system, right? If you've asked this question, if using longitude, why even use north-south? Why not use the regular longitude system? Even that will work, right? But yeah, the reason is, it's much easier to find out where is north and south, right? A compass can basically do that for you, right? rather than knowing, oh shit, where is London? Sorry about that, but yeah, oh, where is London? Like start finding some way. I don't even know how you'd find that out, but okay, yeah. So if you're at the North Pole, yes, that's a good suggestion. You can probably use that, and there is probably some way of doing it out there, but for this general system, they haven't defined it, using longitude. This definition does not work at the North and South Pole. That's all. It's just for testing your understanding. That's the reason I asked it. Okay, I hope that's clear. I'll move on. So I hope equatorial system is clear. I don't know if I have any. Okay, we'll move on. So the ecliptic system, as I said, the Earth is tilted and does not, it's not rotating. That the Earth's rotation is not in the, that rotational axis. Okay, if you think about the Earth as, where's the correct diagram? So if the Earth is, okay, this is a more complicated way of saying it, but essentially the equator is inclined to the ecliptic plane. The ecliptic plane is called the plane where all our planets lie, same plane as the sun and the other planets. That is so you can think of it as the plane of our solar system. Okay, I hope that's clear. The plane of our solar system, basically, our equator is inclined to that. Okay, here we've used our equator as the reference, but there's also another way of looking at it, which is using the ecliptic, the plane of our solar system, as the reference. Okay, so in that case, these two, here they essentially switch positions. So here the ecliptic is like this, the celestial equator is like this. Again, vernal equinox remains the same because it's essentially the intersection. So yeah, the best way, now that I've defined ecliptic and celestial equator, I hope the definitions are clear to you. But essentially, the intersection of both of them, that is your vernal equinox. One of them, at least. The other one, I don't know what it's called. I forgot. Sorry about that. But yeah, essentially the one that happens in March, when the sun reaches there, that is called vernal equinox. That is your reference. Okay, that reference is still used in. Give me a second. That reference is still used in the ecliptic system, and the terms that you use are the ecliptic latitude and the ecliptic longitude. Okay, so yeah, we've gone back to our geography, latitude, longitude. So the ecliptic longitude has the same reference as right ascension, mainly used for planets and other bodies in the solar system. It's I did say that everything lies in the same plane, but there are slight variations. We make a generalization actually that everything lies in the same plane, but there are some like very small angles. There is a slight difference, and so then you'll say but how will you define the ecliptic then? It's just the plane that contains the sun and the earth. That's it. All right. So yeah, most planets just have a negligible inclination to the ecliptic. So let's say this use case is much more prominent in for something like a comet, right? A comet coming in, you can it's within our solar system. It's a nice way of defining where it is. This is where this is just one of the use cases that I'm saying. And also here the center is still the earth. Okay, there's also the heliocentric ecliptic system, but I am omitting that here. But essentially I think the same, okay, not the same, but probably something, how you'll define the ecliptic longitude, the reference will probably be something related to Earth. I'm not entirely sure. Don't quote me on that. But yeah, but the entire gist here is everything is just spherical coordinates. You just need to find out where is the reference. That's all. It's not more complicated than that. Okay. So finally, the last system. Let me just check the time so that I pick up pace accordingly. The other equinox is the autumnal equinox. Exactly. Thank you very much. Yeah, okay. I think we are at good pace here. So the galactic system. The solar system essentially lies in a plane. Well, guess what? Even our galaxy is like a plane. Okay, it's not exactly, but most of the matter that's present, most of the objects that are present, they lie roughly along the same plane. So if if you're looking at things within the Milky Way, above it, where it is, blah blah blah, like, because even though I said, like, most of the objects lie within the Milky Plane. I mean, sorry, the Milky Way, the Milky Way galaxy's plane. There are a few things which are above, especially things called clusters, star clusters. Some of them lie above, below it, blah blah blah. So this is where this is used. And here the reference system is the galactic plane. The sun is the center here. Okay. It's not the heliocentric system. This is different. Here we've taken the reference plane. So while defining any system, right? If you want to make some coordinate system that you use for astronomy, let's say you want to make one, okay? Whether it sticks on, you don't know. Like, try pushing it, create like a page for it, change our coordinate systems, blah, 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 whatever. If you want to change it and you want to make your own, you need two things. You need a reference plane, a well-defined reference plane, okay? That, even though the first one, it changes with location, but depending on your use case, okay, you can choose it accordingly such that the reference plane does not change, easy to identify. And then you need another one for the longitude, okay? You need two references, that's all it takes to define a coordinate system. So if you want to make your own, go ahead, whether it sticks on or not, that depends on people and how useful your coordinate system is. So yeah, it's called the galactic latitude, galactic longitude. I hope this is clear. Let me just check for questions. And let me take a 2-minute break. I'll just take a sip of water and come back. In the meanwhile, you can ask any questions in the chat box, obviously. Yeah, I'm back. Sharp at 10:30. Let's commence. If you guys want a break, you can tell me. But I don't know. What do you say? I think it's just 30 minutes more. Like, just sit tight. Hopefully, it's still interesting to you. But if it's not, like, we can have a short break, 5 minutes, and come back. Okay, I'll continue then. So units and coordinates using AstroPi. So there is a reason why I taught you all this, apart from just engaging in some your astronomy journey, finally understanding the coordinate system. You can actually use it for some interesting things in AstroPi. So we can use AstroPi to work with these coordinates. Makes it very convenient, especially because regular. If you just let's say you're doing some calculations, and you define some variable RA. You put in the value some 270, and then you take another variable dec is equal to 25. Okay, then you perform some operations with them. Well, you're just storing them as integers here, right? Integers, or depending on what language you use. Well, I'm restricting myself to Python, but it dynamically assigns some data type to it, right? Depending on how large it goes or whatever. But it'll essentially give it, some float value or something. And then if you add, like, to that 270, the right ascension, if you add, like, let's say some 120 to it, well, it'll give you, it'll give you 390, right? 390, well, not that useful, in your calculations. You'll have to perform unnecessary conversions, like, divided by, take the mod with 360 to get, actual thing, blah, blah, blah. Rather than that, AstroPy, does everything for you, and you can actually define the units clearly. So let's import, the specific, modules or sub packages or whatever. So I import, as I said, don't import the whole thing. Just a rule of thumb, if you can import the whole thing, if you're, if you're trying to be cool, but usually it's recommended not to. So let's import units because you're going to use that. Then from AstroPy coordinates, import sky coord, earth location, and altaz, which means altitude azimuth. Then from AstroPy.time, I'll import the time module as well. So let's AstroPy.units handles defining, converting between, and performing arithmetic with physical quantities such as meters, seconds, hertz. As you can see, like, it. Okay, yeah. One more thing. Apart from just calculations, let's say you want to print some, let's say some quantity. Some. Let's say you're dealing in kilometers. Okay, you want to print that value. You'll always have to write, some print statement and append km at the end, km or kilometers, whatever, some string at the end, right? That's it might seem like a minor hassle to you, but why not just standardize it? Create some, something beforehand that assigns some, it keeps the unit information intact, basically. So here we use AstroPy.units. So you can define multiple units. Okay, this is not just restricted to like degrees, RADEC, blah blah blah. So here we do quads is equal to sky quads. So essentially u dot degree, right? So I've imported this units package as u. So u dot degree essentially defines degree. Okay, like it defines the unit degree. And if we use this syntax, we multiply it with some number, we essentially create some object, you could say, some object. I don't exactly know, but I'm pretty sure this is an object. It's treated as an object, and this object is, you can think about it as 12.11 degrees. Okay, where this object is used, it'll only be used in AstroPy again. You can't use this in some other package or something because this object is created for AstroPy. But this object is very useful in terms of when using AstroPy. Okay, so 12.1 degrees, 85.26 degrees. Okay, this I put it in sky quad. Okay, this is the syntax. Then I basically, print what is that? What is this object that I've created? Sky quad. This quads. I've called it quads. I put quads in, print it, and this is the object. It's something related, some AstroPy object, sky quad ICRS. Okay. I forgot what ICRS is. I'm sorry. I'll check and let you know. Okay. But basically RADEC. So it talks about this is RS is a reference system. Okay. I forgot what IC stands for. If one of you can check for me, and then I'll talk about it. But RADEC in degrees. So essentially, when we use sky quad, we're starting off with RADEC. Okay. And depending on the value we put, doesn't matter. It assigns the RA in deck. Okay. RA comes first, deck comes second. Okay. Right ascension, declination. Don't forget. So it has so this object has two attributes. Yeah, right ascension, declination. We can also retrieve these values in different units. So quads.ra. So this is okay. 1 second. I'll need to start from here. This, then this. So this has printed in degrees. Okay, this right ascension is in degrees. I did say before that they use the convention of hours, but you can use whatever. They're essentially the same thing. And if you want to, if you're working with that convention, why not do this? This is in hours. Okay. So this is the way you can easily convert between units rather than writing a conversion, right? So this is one of the ways to do it. So here do not get confused though. Here quads, from quads I'm taking the attribute RA, then I can put a dot R at the end just for unit conversion. Okay, so that's how it works. Then you can do the same for declination, although like that is usually in degrees itself. Let's see if we can do that. Yeah, you can do that. It's just a unit conversion, so nothing's stopping you. But whether the convention is that way, that I can't say for sure. Okay, usually it's just for RA. So let's keep it like that. All right. Yeah, this is the way you do it to convert between units. Transforming from one system to another can be done using transform to. Okay, so here this is a very convenient thing. As for the math behind this conversion, I thought of omitting it, but if in case you want to know, you can check it out on your own, or I'll probably give you some supplement. Okay, so chords.transform to, very simple syntax. So the keywords here are different. So this is where the ICRS comes in, right? In case you want to go back from galactic to the RADEX system, the eclipse, yeah, the equatorial system. In case you want to go back to that, rather than typing equatorial, I think you type ICRS. I'll confirm that. Okay. So to transform to galactic, this is what you do. It's very simple. So as you can see, there is some conversion happening here because there's a lot of difference here. 12.1, 122, and 85.26 becomes 22. So yeah. At the same time, you can also define altitude azimuth. We'll get to that. Okay. So what if we want to transform chords to the horizontal system? Okay. As I said, another question for you. What do you think? Can I just do transform to alt as, or whatever it's called, chords dot transform to alt as? What issue will arise? Can someone tell me?
We don't have a reference point for it.
Yeah, by reference point, what do you mean?
As in the reference plane, as in the point where we are
Yeah,
standing at.
exactly. We don't have our location on the earth, right? As I said, horizontal system depends on where you are. So for that reason, converting to horizontal system is a bit more nuanced. So here, here I've taken values from, okay, were these values accurate? I'm not entirely sure. I think they are. Might be, okay. Probably are accurate. So these are the latitude and longitude for Chennai, okay, specifically IITM. I think I went to Google Earth or something and found it out, but hopefully this is correct. The height is definitely not. This is just some random height I put in meters. So here you use Earth location, okay, to store the latitude, longitude, and height. Okay, this is the way you store. You can store it in this AstroPy, and I've stored it in this object called IITM. Then the time also matters. Okay. Why does time matter is because basically I think the stars. So let's say you're observing a star. Okay. Today I observe it at some latitude, longitude, blah blah blah. Now 1 month later, the Earth has changed position because it's revolving around the sun, right? The star will be located at another location. If I just put in, this regular latitude, longitude, maybe I'm looking at the same place, but the star might not be there. Okay, which is why we need to also correct with time. So here, so the time essentially is like, well, what we do is for getting observation time. Here, this time when we put this in, so here, why have I done this minus 5.5 hours is basically because this date that I put in, this date is fine, but this time that I put in is defined according to GMT, I think most probably. Okay, that is the one that it corresponds to the Greenwich Meridian time. Okay, but the issue here is we are um, we are 5.5 hours ahead. Okay, wait, are we ahead? But okay, whatever, doesn't matter. But basically, this is not our IST time. Okay, in case we want to find out our proper time, like let's say we observe it at somewhere what we observe it around 6 p.m. or something. Okay, 6 p.m. Yeah, 6 p.m. or something, right? No, 8 p.m. Let's say we are observing it around 7:30, 8 p.m. Okay, if we are observing it around that time, we need to convert. Okay, this is not what. This will be around 5 p.m. then. Sorry, my bad. So around 5 p.m. or something. It doesn't matter. Let's say we have some time. We have to put in the regular Greenwich Meridian time because this is how the convention works for AstroPi. And then to that, we need to correct accordingly based on our location on Earth. Okay, based on how the time zones work. Okay, if you want to observe at 8 p.m., you need to correct it and convert it into the time for you know the time used by the Greenwich Meridian or whatever. Okay, I might have confused like whether this time. Okay, so okay, my bad. So the actual explanation is, let's say I'm observing at 10 p.m. Okay, this time is whatever I input. Okay, let's say I'm observing at 10 p.m. But the AstroPi actually uses, it calculates the locations and stuff accordingly, according to Greenwich Meridian time. So this is the actual explanation. I'm really sorry. We are 5.5 hours ahead. Okay, that's why it's for us when it's 10 o'clock. It's actually somewhere around 4:30, 5 o'clock for them. Okay, for people at that particular location where the time zone is defined. So we need to correct for that. We need to subtract 5.5 hours. Okay. If you're observing at 10 p.m., this is where you put it. I'm observing at this time, but since AstroPi uses, will it show here what it uses? I don't think it does, but okay, it uses like it's called GMT or something else. Okay, but whatever convention it uses, we need to account for that, and then essentially we get the time value. Okay, this time value we put it into chords.transform to alt as. Okay, this is where we finally use our altitude azimuth system. So depending on the time and location, we put this in, and so the time thing arises because of the, don't forget, it arises because of the rotation of the Earth, and as well as you could say like the revolution of the Earth around the sun, but more so because of rotation. Okay, because even during the same day, right, the Earth is rotating and your plane is essentially moving, which is why the coordinate of the star changes or whatever. That's why you need to correct for it. So that's why we put in some observation time and we put in the location. We created we can change it into, we use this alt as you know we use this alt as object, you could say method or whatever, and then we use the transform too. So just to take a step back, in case you're slightly confused with my mess up here. Quartz right now is something in RA and deck, okay, in the equatorial system. We want to convert it into horizontal system, but for that we require the information about the time as well as location, your geographical position as well as time of the day, because the Earth rotates. Okay, for that we need to specify two things: the location as well as time, in order to convert it into the altitude azimuth system. So essentially, instead of just writing, something like, you need to specify the location as well as time. So that's all this is. We use something called alt as, specify the time, specify the location. This accordingly converts it into that altitude. So at this date, so this session was last year, right? So that is the reason why I've used 11 July, and that's when the session happened, I think. 11 July at 10 p.m. If you were at IITM, where would you observe this whatever star that I've taken here, which is at these coordinates in the equatorial system? Where will that star be according to you? The altitude is at 13 degrees, and let's print. I've called it, so I've transformed it into altitude azimuth. I've stored it in quads underscore h. Okay, quads underscore h. This is how it works. Okay, wait. Is it azimuth? Oh wait, sorry, I need to. So it takes a bit of time. Okay, that's taking a lot of time. Did I screw up somewhere? Okay, no, it worked out. And yeah, so this is the azimuth. Okay, they've used it in the days minutes convention, but yeah. Oh, sorry, this is still degrees. My bad. This is at 4 degrees, 16 minutes, blah blah blah. These many seconds, and this is at 10 degrees. So yeah, this is how you compute it. So instead of displaying both, let's do this. Just the altitude. The altitude is at 10 degrees, 59 minutes, whatever. Okay, this is the way you convert to altitude azimuth. I hope that's clear. Sorry for the fumble in the middle. Now we're almost done. So let's talk about filters a bit. So images of astronomical objects, as I said, as I foreshadowed at the start, these images are not just taken by, like regular cameras, just whatever you see in the optical region that, gets, you just store all that intensity. And there's the, essentially so based on the pixel value, right? Based on the pixel value, it assigns it to uh, the color to it. So there'll be some range for, red color, there'll be some particular range. For black, there'll be some particular range. That's how a regular thing works, okay? But here, for astronomical images, we use something called charge coupled devices, okay? You can think of them as a modern day equivalent of photographic film used in old cameras. So why they're called charge coupled devices is something like they contain these very small units, okay? They're an array of these small units, and whenever a photon hits one of these units, these very small units, it essentially creates some kind of excitation in them, and that excitation, based on the excitation energy, it stores the pixel value. It converts it into some pixel value, and it stores that intensity value, okay? Essentially, this intensity value does not contain any information about color, okay? So this takes, like, in some sense, it takes black and white pictures, okay? What you can do is you can interpret this pixel value based on the filter you've used, based on what region you're observing, okay? That is where you bring in color. On its own, there is no definition of color, because if your telescope is observing in, the infrared range, what color do you assign to that, right? If you're observing in, x-rays don't have color. Color is a human term. There's no, like, concept of color. Like, there's no universal concept of color. Even even between, like, person to person, colorblind people, they have no concept of certain colors because they can't observe them. So imagine, like, a few years down the line, something happens, everyone forgets, human history, and people only have people forget the concept of the color yellow, and they can't see yellow anymore. They'll never create yellow again, because there is no need for it. Whatever colors you see, those are the colors you'll define. Okay, color is just a human concept. So essentially, the photos taken by the CC3 is just, you can just think about it as black and white. Even black and white is not the right way to think about it. It's just pixel values, and you assign color to those pixel values based on the filters you've used, if you've used any. So here, I hope this picture is a bit small, so I'll pull it up here. But essentially, these filters, they are not discrete wavelengths. You're not observing at one particular wavelength. Rather, you can think of these curves as the amount of intensity it lets in. Okay, so for this much range, for this range, so is there, yeah, for this range of wavelengths, so 3000 to 4000, let's say, that's like almost, it's close to red, goes into the infrared a little bit, but it's close to red, right? 400 to 700 nanometers, that's the optical wavelength, right? Or here it's in Armstrong, but whatever. So here, for this range, 3000 to 4000 or 300 to 400 nanometers, all the intensity that comes in it'll detect it. Okay, but for stuff at this wavelength, at where it peaks, it's more sensitive to those intensities. As you go further and further away, it's less sensitive to it, but still it detects. And after one point, it completely blocks out those intensities. Okay, here at the peak, it lets all the it lets at that peak whatever wavelength comes in with this matching wavelength. Okay, it'll let in all of that intensity, but for any wavelength which is not at this peak, it'll not let everything in. It's not as sensitive, and after one point it's zero sensitivity. Okay, that is how you define it. And different so these are names of surveys. Okay, these are like SDSS is called the Slow and Digital Sky Survey. Essentially they have a telescope which is mapping out the sky some particular location, and they have their own convention of filters. Okay, so their convention is called the UGRIZ convention. UGRIZ. U is red, G is almost blue greenish. R, even though it's in yellow range, whatever it's called, R. I, Z, doesn't matter, but everyone defines filters differently. Okay, you need to check this when you're actually using the filter. So here here this thing uses a more demonstrative, it uses more demonstrative filter names. 336, I'm guessing, is because the peak value is at 336 nanometers. Here it's at 439 nanometers, which is why probably they've defined it that way. But yeah, maybe not the peak, but the center. Okay, so this is about filter. Okay, it lets in this much wavelength in this range, and beyond that, it doesn't let anything in. And it's useful because if a star, when you say a star is blue, okay, the reason it's blue is because maybe if you observe it in this blue filter, you'll see a lot of intensity, and in the other filters, it's not as intense. Okay, that's why you call the star blue. That's all. The star itself, the star itself may be emitting in like a wide range of frequencies, but you're observing a lot of intensity in the optical range of blue. So that's why you call it a blue star. That's all. So now some photometric concepts. Uh, sorry, photometric concepts. So specific flux. So the amount of energy at wavelength lambda traversing a unit area per unit time. Okay, that's the flux. So flux is per unit area. Okay, don't forget that. It's denoted by the small f nu. That's the symbol nu, and this symbol nu is there because this is specific flux. Okay, this is not just your regular flux. The units are, as you can tell probably by the amount of energy. So watt multiplied by the unit of time, which is here hertz inverse. Okay, or whatever. So actually it's energy per unit time, right? That's why it's becoming watt. So yeah, and then per unit area, the meter square. Okay, then second, okay, I guess this is a small, hmm. Okay, this is not rendering properly, but uh, okay, for some reason it's not rendering properly, but whatever. So the flux is the total amount of electromagnetic energy per unit time per unit area. Okay, so here it's like restricted to a particular wavelength, the amount of energy, but general flux is across all wavelengths. That is denoted by F or capital F, whatever the regular units. Okay, so this Hertz inverse arises because it's in one particular frequency. So next we move on to luminosity. So these are two important things: flux and luminosity. You'll see it a lot in photometry, like spectroscopy, photometry, blah blah blah. So bolometric luminosity or just luminosity. I don't know what bolometric means exactly, but it's used in some books. But it's essentially the same as luminosity. Okay, so the total amount of electromagnetic energy emitted per unit time. Okay, so here there's no per unit area. That's the distinction here. So how you should think about it is, let's say you have a star. Okay, the star at the surface, you calculate some luminosity. So essentially, it's just the power of the star, you could say. the amount of energy it emits per unit time. Now, when you're very far away from the star, you will detect flux because wherever you're located, like you put in some, you have some detector. Okay, that detector has some area. Now, all this luminosity, you could say, that's not whatever. All this luminosity is not falling on the detector, right? The luminosity, if it's an isotropic source, that means it emits in the same intensity in every single direction. It'll basically fall off as proportional to 1 by r square, right? A candle, although a candle is not isotropic, I think, but a star is probably isotropic. It's spherical, it'll emit the same intensity in every direction. So the amount of that power gets distributed across a shell, and the shell, as you move farther away, it gets larger and larger. So for a particular area, right, a particular area on the shell, the amount of energy you detect gets smaller and smaller. So that's what flux is. Okay, so let's say you detect the flux for this entire area, this entire sphere. That will essentially be equal to L itself, right? Because the energy is not going anywhere, assuming it's not decaying as time goes on, or as distance, as it goes through distance, as it travels some distance. Okay, in case it's not decaying at all, the luminosity doesn't change, just that our flux changes. And if you multiply the flux with the area, because flux is per unit time, you get back the luminosity. Okay, that's how. So when we are at Earth, we detect flux because we don't know the entire luminosity. But based on that flux, we can detect, if we know the distance to that object. Okay, so let's say we have some object, 4 light years away or something like that. We detect the flux. Okay, the flux that we experience, and then assuming that the same flux is it's an isotropic source, so the same flux should be experienced everywhere, no matter if I'm here. I hope you can see my cursor. Okay, so no matter if I'm here, I will be able to detect the same flux. So if I just multiply that by 4 pi r square, okay, because it falls away spherically, blah blah blah. If I know the distance to the object, which I calculate through other various methods, or I can, if I know luminosity and I have flux, I can calculate distance, whatever. If I have two knowns, I can calculate one unknown. That's the point here. And usually flux is the known here. So if I have the distance to the object and I have the flux, I can calculate the luminosity. Luminosity is very useful because it does not vary with distance. I mean, like, that's not the right way to say it, but it's the amount of energy the star emits. So that's why it's a very useful quantity. So, sorry. Yeah, so notice how F falls off with 1 by r square for a fixed source, for a fixed isotropic source actually. So next is the concept of magnitude. So in case you've again done a little bit of astronomy before, you may have seen the brightness of stars being measured in terms of magnitude. Okay, so how do you define this magnitude? Apparent magnitude is defined by the following formula: m is equal to minus. It's a logarithmic thing. Okay, so why logarithmic? I think there's some historical reason behind it, but it works the best. Okay, I've kind of forgotten. This magnitude system was started a very long time ago, and logarithm makes sense because usually, like, you can, if an astronomer says, a star is 10 times brighter than the other, uh, in terms of flux, it can mean a different thing. In terms of logarithms, it can mean a different things. That's the reason. Okay, so a 10 times, 10 times brightness, 10 times brighter might mean 1 unit in magnitude. Okay, so let's say if I have a magnitude of -3, also there's that minus sign. Okay, so if I have a star of magnitude -3 and another of -4, you can say that the star with the magnitude -3 is 10 times brighter than the star with -4. Okay, so the negative sign it changes a lot. Okay, if this negative sign wasn't there, then the 4 would be more brighter than the 3. But since it's -3 and -4, -3 is more brighter than -4. Okay, don't forget that. So as it gets closer to 0, it's brighter. Okay, but this is apparent magnitude. Okay, this apparent magnitude is measured with respect to something else. So that's the point. Like if you have some reference star, you can measure magnitudes with respect to that star. Okay, you can create a whole catalog with respect to that. But again, this issue of references arises. Like why use a reference? Why not have something absolute? Okay, so to circumvent this issue, like it's kind of like almost cheating, but we define some sorry, we define some some value, some flux value. Okay, flux value or some luminosity value. You can do that conversion. It's essentially like some star located at okay, we'll get to absolute magnitude, but instead of using some f naught apparent magnitude, just remember it's relative. Absolute magnitude is not relative. Okay, so magnitude has no units. It's just usually written along with the suffix of magnitude. So here, this point again, it's not loading for some reason. Yeah, so absolute magnitude is defined to be the apparent magnitude an object would have if it were located at a distance of 10 parsecs. Okay, so essentially you can convert between this apparent magnitude to absolute magnitude by treating it as if this flux value that you calculate, like this reference flux. So this is the flux that you've detected, this f. Okay, sorry about that. This f is the flux you've detected. You usually use some reference, right? This reference you have to treat it as something which is located at 10 parsecs. Okay, which is why you can you define luminosity, since you're using a fixed distance here. So if you use that, you can use this relation to calculate the absolute magnitude, and the absolute magnitude doesn't depend on reference. So I can talk to you in terms of absolute magnitude. If I tell you like I have a star of apparent magnitude -3, doesn't make that much sense, right? Because you have to then ask me, oh, what's your reference? The reference that I select, that is assigned 0. But here in absolute magnitude, there is no need for a reference. You can just directly say, call out values. Some this L this L circle. Okay, it's some fixed value. Some convention is used, but yeah, essentially this is an absolute scale. That is a relative scale. That is all. So astrophotography demonstration will not be followed. This was last year. I'm sorry about that. So yeah, I think we've reached the end. I hope we are on time. Yeah, I've gone 5 minutes ahead, but that is the end of this session. I hope it was useful to you. I hope this this generates some interest in you, and you can explore a lot more. There's a lot of documentation online. All of this is well documented, and you can play around with AstroPy, and with this knowledge of coordinate systems, you can do a lot of cool things. And yeah, that is all. If you have any doubts, I'll be happy to take them up. Yeah, so Krishna Balaji told put in what is ICRS. So International Celestial Reference System. So let me just verify something. In case now that I have, let's say this, I'll call this so quad underscore G. So I have these galactic coordinates. Now, if I want to go back to our equatorial system, I type. If I type ICRS, it okay, it doesn't work. I think if okay, equatorial works, I think. Oh wait, no, equatorial also doesn't work. Or do I have to load this? I've loaded this. What does it say? Transform frame must be a frame name, class, or instance. uh, transform underscore 2, everything's fine. Why isn't it working? What is chords of G? Yeah, why? I wonder why, but basically, as you see here, right, this says galactic. Instead of galactic, if you want to go to equatorial, I think you have to use ICRS. That is the thing. They've just used a different name, and probably equatorial system is also referred to as the what International Celestial Reference System, right? Yeah. During the semester, yeah, definitely. We plan to have a lot of astrophotography sessions, and since things will be in person, you can hop on, come to the terrace, HSB terrace, and we'll do some live astrophotography there. Take a few pictures of the moon, and maybe even usually we take pictures of planets as well. Yeah, astrophotography session during the semester, definitely. During the summer school, I'm not entirely sure. We'll have to discuss with the club member. So yeah, any questions? Okay, this worked. So it wasn't. It was the capitalization issue. So you just type ICRS. It'll convert back to equatorial system. It's just a different name. That's the mystery here. Okay. Yeah. Any questions? Yeah. Yeah.